Okay, so as promised, today we are doing renormalization group. Okay, this is a technique. We're going to see that some of the techniques that we have learned, for example, Feynman diagrams, they're very useful when doing this renormalization group technique. As far as I understand, people understood the need for such a method already when QED was developed, which is pretty early. But the modern and full understanding of this was only developed by people like Kadnoff, Migdal, Wilson, and Fisher in the 70s. It became very, very popular. I think the first problem that was applied to successfully is known as the Kondo problem, and immediately became useful in many different techniques. So the basic idea behind OG is, okay, let me write the organization group OG. Okay, so the basic idea is that we have a theory, let's call it S, with some couplings, let's call them J, okay? And this theory lives in, I don't know, some domain, some system, okay? And then the basic idea is that there is some sort of short range cutoff. For example, you could imagine that the system is on a lattice, okay? Or there is some high energy scale which defines a short time scale or momentum, high momentum scale. Okay, and this is our theory. And then we want to perform something known as coarse graining. Okay, so the idea behind coarse graining would be that we somehow basically eliminate for example, you could imagine that we take four chunks of the system and somehow find a way to cluster them together. Maybe I should mention before I say that these couplings, okay, J tells us how neighboring. It can be local. It can be a local coupling inside each one of these grains, but it can also tell us something about how different grains interact with each other. Okay, and then imagine that we take this kind of block. People call it a block. You take a block, which is a larger system, okay, and you clump it together. And if you're capable of, after clumping, basically rewriting the theory effectively, such that these larger clumps now have some coupling, which I will denote by J prime, okay? And in this procedure, you make, you come back to the original structure of the theory, just coarse grained. Then you could imagine performing this iteratively or successively again and again and again until you reach the system size. And the idea is that we want to look at how these couplings flow. So you could imagine that here you have some scale, let's call it delta x, and then here we have some scale which I will denote by delta x prime. And the idea is that delta x prime over delta x is equal to some e to the L, where L is some, or B, let's call it B for now. Okay, where B is some number greater than 1, so that we're basically growing. Okay, and the philosophy behind this is that if we follow how this coupling J grows with time, evolves under these successive coarse graining procedures, then we can say something about which couplings are important, which couplings are not important, what tendency to phases there are. And sometimes we can even find new fixed points, which we will discuss, which can even give us more. It can give us, for example, properties of how correlation functions scale, and how order parameters, what's the scaling of order parameters, all these critical exponents that you may or may have not learned about in other courses can be obtained in such cases. So this is the kind of the basic idea. And then if you imagine that we perform an infinitesimal coarse graining, such that B is equal to e to the dl, where dl is a very tiny number, then we can write an equation dj to dl is equal to beta of j. This is known as the beta function. And it tells us how these couplings evolve as we do this coarse graining. Okay, so this is basically what we're after in our G. This gives us the intuition, and we'll see how it works. Any questions up to now?
So you're basically like differentiating J with respect to this expanding parameter. I'm not really sure.
Yes, I am. I want to understand how J. Okay, so the philosophy. Okay, the philosophy is that we have a system. Okay, and we imagine a system of. Imagine that the initial size of each one of these blocks is something microscopic, like the interparticle distance, the interionic distance, or something like that. And then we're performing this rescaling again and again and again and again and again until we reach a macroscopic size. Okay, so the philosophy behind it would be that at very long wavelengths, the low energy and long wavelength phenomena that you observe will be effectively controlled by these J primes, not by these J's. The reason it works is because the theory is self-similar. Okay, everything we did, we do it exactly. You'll see that what we actually do is integrate out the short wavelengths out of our theory. So when we say integrate out, what we actually mean is that we're taking the scattering amplitudes in our theory, and we are dressing them with corrections, corrections, and these corrections are high energy corrections. Okay, and then we get new couplings due to these corrections, And these new couplings are actually only relevant for a theory that's truncated. What do I mean by truncated? It means that it's really only accurate, up to some short distance. So as I coarse grain more and more and more, phenomena that will be waves, if you try to excite the system at a very short wavelength, then these J's won't be relevant for that. They're only relevant for very long wavelength behavior. And that's fine, because many of the physics that we're interested in, like what's the ground state, what's the order parameter, what's the low energy fluctuations of an order parameter, stuff like that, all that is actually controlled by the very long wavelength behavior. So that's good for us, okay?
So
yeah,
kind of looking for an effective theory that works at our size, right? Our like the macro.
So here you're touching upon a different issue, which is when do you stop the RG? Because there are different things that can stop an RG. So maybe let me explain, okay? I just want to explain. Imagine that we have, here I have, this L, and here I have J, okay? You can have different kinds of behaviors. For example, you could have a behavior where this J flows, towards weak values. Okay, so it diminishes under this RG procedure. Okay, and in that case, you can continue maybe the RG forever. And then the only thing that stops you is, for example, the system size or the temperature or, a mass, if there's some mass. We'll talk about that later. But then there are other situations. For example, you could even have a situation where this J kind of grows in this regime, but then there is something which we call separatrix, where on this side of the separatrix, actually J tends to grow in magnitude. And then there is another question, which is when it becomes too large, then the methods that we use are not valid, and you need to stop the RG. So this is called the runaway flow, and it happens many times. So that's another issue. And then finally, I also wanted to mention that you can sometimes have kind of fixed points. So what we see here is like a separatrix that separates, flowing to weak coupling and strong coupling. But you can also have these kind of fixed points where actually the flow is towards, a specific value of this J. This is called the fixed point. Okay, and here is something very, very deep, something that is very important to us in condensed matter theory, because as you know, most of the theories that we study are very simple models. Okay, they have, it's like a Gaussian theory, phi to the fourth field theory, fermions with four fermion interaction and stuff like that. And you could ask like a natural question to ask, and I don't know if you've ever asked yourself, but like, why don't I take like 6 body terms? Or I mean like 3 body terms, 4 body terms, 5 body terms. Why don't I take like all sorts of weird interactions that you could imagine? Like why do I stop and like with quartic terms? Why do we write these theories all the time? How is it generic? And this RG is actually something that gives us a tool to argue rigorously for when such terms are, when such theories are rigorous. And they're rigorous under the sense that it might be that you have many different microscopic theories, okay, that are different in their microscopic behavior, but eventually they all flow to the same universal fixed point. And this is something very deep, and then that gives merit to study the properties of such a fixed point. Such a fixed point suddenly becomes much more important than just another theory. It's actually a theory of many, many different problems, okay? And another thing that is kind of generic is that we can find many times that completely different systems that have completely different physics, for example, spin degrees of freedom, you know, that are like with spin orbit coupling, so you get some symmetry breaking, and they behave like an Ising model. But then you can also have, I don't know, like a nematic transition that looks like Ising, where you break symmetry, and you could have ions in a trap that create a structure that is staggered and is also Ising-like. And all of these different models, they can have very different, you know, physics in the microscopic scale. They're completely different particles, completely different degrees of freedom. But in their low energy and long wavelength behavior, they all are universal. They flow to the same fixed point. So this is a kind of maybe one of the most important reasons or most important contributions of RG. It gives us a rigorous method to analyze when is a theory or what kind of models would have what kind of behavior, and it also helps us narrow down significantly the number of theories we need to solve, right? Because you can you know, instead of solving every different point in phase space, you just choose the fixed points, because any other place will flow away as you do the RG and finally arrive at some fixed point. So this is kind of the general idea. Okay, any other questions?
Just like more technical question. You do not mean when you wrote beta, you do not mean like the beta function, right? It's just like you notice this as beta, right?
What do you mean the beta? You mean that there is in math there is a
like gamma function. It is not. It's not this, right?
No.
Okay.
It's just it's for every model or theory you're going to have a different beta function. And typically we don't obtain the full beta function. It's very rare that one can obtain the full beta function. Typically what we have is something like a expansion, a power series of this function. Okay?
Okay.
Okay, so let's see a simple example. So, which is the transverse field Ising model. Okay. So, has anyone encountered the transverse field Ising model?
Yes.
So, Joseph, you've seen the transverse field Ising model. Anyone else?
No.
So, this is maybe the simplest possible model of a quantum phase transition. Okay. it looks like this. So I'm taking the interactions to be ferromagnetic. And then there is a magnetic field H. Now, the point is, because this term and this term do not commute with each other, this model becomes essentially quantum. Okay, it means that even in the ground state, you can have what we call quantum fluctuations. So in the limit, if I look at the phase diagram, I draw J over H, or maybe actually let's, in preparation for what we have, let's write J, H over J, okay, and say here I have, 1, then, okay, here I don't know what's gonna happen, but, if I go to very, very large H, then all the spins are kind of pointing in the X direction. And in the other regime, where H is much smaller than J, we have all the spins, say, pointing up, or all the spins pointing down. Okay, this is and it turns out that one can use something known as a Jordan-Wigner transformation to map. Okay, so I might even give you an exercise on that. Jordan-Wigner transformation. The Jordan-Wigner transformation maps these two terms to each other, and therefore we can conclude that if there's a phase transition, it must happen here at 1. Okay?
What is 1 again?
H equal to J. Clear? Okay? So now let's see how we perform such an RG. Let's assume that we're in this regime here. So to see how the RG works, let's assume we're in the limit of J much, much greater than H. Okay. Now, what we imagine is, imagine that we have our spins sitting there. Okay, in different sites. And now we basically block them. Like I said before, each pair we put in a block. Okay. And so initially, right, we had J here and also J here. And in each one of them, we had a magnetic field H, right? So let me write the block Hamiltonian, the Hamiltonian of the block, okay? And but let me define 4 states. Define a block made of 2 neighboring spins. And write with the following states. So I'm going to deliberately write the terms in terms of high energy and low energy terms. So the low energy terms, I denote them, it's this, and this. The high energy states, E1, no, is up, down, and E2 is down, up. Okay, and then I can write the Schrodinger equation, the block Schrodinger equation is given by, so we have this, minus J, 0, minus H, minus H, 0, minus J, minus H, minus H, minus H, minus H, J, 0, minus H, minus H, 0, J. This thing is up tilde, down tilde, E1, E2. Make this a bit more efficient. Now the idea is that if you look at this spectrum, then you see that there's a huge gap, right? There are two states, two low energy states that are at energy minus J, and two high energy states that are at energy J. So if we're looking for the low energy, okay, physics, then we can basically eliminate these high energy states from the theory. Then you see that each one of these blocks here retains the same number of degrees of freedom, or the same Hilbert space, if you like, right? Just two states, because we eliminated two of the four states. And therefore, I'm ensured that I'm going to, still have an effective spin degree of freedom, okay? And the only question is, what kind of effective theory do I get when I think about these block spins? Like, how are they coupled? What is their model? Okay, so to do that, I'm going to eliminate from the Schrodinger equation, I want to eliminate the high energy states. So it's very straightforward to obtain, if I solve the last two rows in this matrix equation, I can isolate these excited states, and I find that they're equal to minus H, E minus J, and this is tilde, it's down tilde, and same thing for the excited state 2. Okay? Now, the next step would be to plug these equations in the remaining two equations. The remaining two equations. So what we get, is that clear? Any questions up to now? No questions. Okay, good. So if I
E1 is equal to E2 in this representation?
You see, this is kind of like, yeah, first of all, yes. Basically, what it's telling us is that the virtual occupation of E1 and E2 is equal. And there's a symmetry between them. So there is no reason why they should be, occupied at a different level. You see, this kind of factor of H over E minus J is kind of like a perturbative, it's like a perturbative term where you live in this low energy effective manifold and you can hop to the high energy manifold and back down. That's basically the physics. You'll see it more clearly in a second. But the fact that they're equal is just telling you that it's really the same. Like there isn't even a difference in the phase when you jump to these high energy states. Okay. Now I plug these equations in the two first rows, and I get minus J minus H bar H squared divided by E minus J times up tilde plus H squared over E minus J down tilde. This is equal to E up tilde. And we get exactly the same equation for the down tilde. Hey, guys. Okay, so now, first of all, I want to argue that this is negligible, but that's less important. But if I look at this equation, you see that, okay, you know what? Let's forget about that comment about that's not important. Yeah. Yeah.
I'm sorry, I'm not that concentrated at home, but I'm not sure how did you go to these equations from the matrix? Like, is it just a simple algebra?
It is simple algebra because each one of these rows represents an equation, right? A linear equation.
Yes, yes.
Okay. So imagine that I take these two rows, multiplying this equals that. And I isolate E1 and E2. Then I get these two equations.
Okay.
Then I take these and I plug them in these two equations. Okay?
Okay, good. And then you
And then I
subtract.
get this.
Okay, so, okay, good.
Now, what you see here, basically, is a new local Hamiltonian. Okay, you get a new local Hamiltonian, which is something like this. So let me first go back to this theory for a moment. You see this theory? This theory has two types of terms. There is terms that connect neighboring sites, and there is the local Hamiltonian term. Because this term and this term are degenerate, they actually only shift the energy. So you can rewrite this thing as something like H bar over E minus J down tilde is equal to E tilde up tilde and H squared over E minus J up tilde equals E tilde down tilde. And where this E tilde, sorry, E tilde is E plus J minus H squared over EJ. Okay, and yeah, and the structure of this Hamiltonian is basically something like we get minus H, let's call it H tag, minus H tag, right? Up tilde, down tilde is equal to E tilde, up tilde, down tilde. So what this implies is that we found that the local part of our effective Hamiltonian is this H prime guy, which is exactly minus this thing. Okay. Now, if we think about what is the coupling between these spins, okay, if I want to write, you know, the effective J between these blocks, okay, then you can convince yourself that each block like this still has an energy J. So for example, if this spin here is like up tilde, and this is say down tilde, then you're gonna pay a price J. And if they're in the same direction, you're gonna gain an energy minus J. So all this is coming to say that I want to argue that H prime, the renormalized Hamiltonian, is going to be you know, sum over J prime, sigma, let's call them sigma prime, sigma, no, let's call it sigma Z J, sigma Z J plus 1. Let's imagine that these spins were renormalized. They're like effective spins. And then I have, this is minus, and this is minus H prime, sum over J, sigma X tilde J, where J prime is equal to J and H prime is equal to H squared over J minus E. Okay, now in principle, I want to remind you that we're looking at the low energy effective theory. So E is basically negligible compared to J. So what I want to argue is that we can think about this as H squared over J. Okay, so that's what we found. We now found how the couplings change under this RG transformation. Okay, and we can even make this into an RG equation, right?
Wouldn't it be like a minus? H tag is minus H squared over J.
Why minus?
This is how we defined it. It is there is a minus in the.
No. I absorb the minus into this denominator.
Ah, okay.
Here the denominator is switched.
Mm-hmm.
It would be very problematic if it would flip sign, because
Yes.
that each step of the RG, it's flip sign, and I cannot write an RG equation.
Mm-hmm.
Okay, but this is not the case, luckily for us. Okay, so we can write RG equations by defining, you know, let's define. Okay, let's say let L denote, not L, okay, L, denote the RG step, then we can write something like HL plus 1 minus HL, right, is equal to HL squared divided by J minus HL, which is actually HL over J minus 1 HL. Okay? And now, without loss of generality, let DL be equal to 1. Okay? So basically, I'm thinking about each one of these steps. So imagine, for example, we're in the limit where J is much, much larger than H. And let's assume you start at some value. Well, you're going to get some sort of, so this is L, 1, 2, 3. Then you decay very, very quickly, right? Basically a decay like this. And now what I want to do is I want to define a slope. So this basically is my DL. DL is equal to 1. So all this is to say that this reminds us of an RG equation. The HDL is equal to H over J minus 1 times H, and the JDL is equal to 0 because nothing happens to J under this RG transformation. Okay? Now let's plot what we have. So here we have H over J. Here we have the point 1. And the regime of validity that we're in is this regime. And we find that in this regime, right, the flow is towards even a smaller h, right? Now, if you believe this RG equation beyond the limits, oh, what happened here? If you believe this RG equation beyond the limits of its validity, then there is a putative, what's going on? There's a putative quantum critical point here, right? Because basically the flow that we get is towards this direction, as long, because you see this thing is negative as long as H is smaller than J, but once it becomes larger than J, we have flow towards the other direction. And in fact, despite the fact that we derive these equations perturbatively at large J, they turn out to be correct. Like they capture the right position of the critical point, but they're actually only valid here in this regime. And they basically show us that as you coarse grain more and more and more, these quantum fluctuations of the blocks of the spins become less and less important. And this actually also has a lot of physics in it because, you know, when you have microscopic degrees of freedom, they tend to tunnel quite often, and you get these superpositions. But as you block more and more spins, they basically become these kind of heavier classical objects, and therefore these huge block spins, their chance to basically flip becomes very small. So what we typically have is, you could imagine that if in the original model we had this, you know, or that locally, and you could hop between them, now what we have is something like, you know, a block spin is something like this, and then to really hop between these, you know, what you have a lot is kind of hopping to one of these high energy states and then hopping back down or hopping like that. But to do that, you actually need to go through two steps like that. And you can imagine that as the block is becoming larger and larger and larger, these quantum fluctuations are becoming weaker and weaker and weaker. And that's really what this RG transformation is telling us. It's telling us that at low energy and long wavelengths, this theory is essentially becoming a classical Ising model, and the quantum fluctuations induced by the transverse field go to zero. Okay? So that was an example. Now let's do the real deal. Maybe I'll make a comment. So first of all, just to make a connection, what we found here is that beta H of H is this H over J minus 1 times H. Okay, just to make a connection. And I divided this behavior. So here, you know, in this regime, you have beta of H smaller than 0. And this is what we call irrelevant. Relevant. And if beta of H is larger than 0, it's relevant. Why? And here, at this point, beta of H is equal to 0, and this is what we call a marginal perturbation. Okay? Questions about that?
This is everything happening at 0 temperature, right? It's only quantum fluctuation.
Well, temperature. Let's see. You could, there are ways to argue that you can continue this same method for finite temperature, just temperature sets a cutoff. But that requires some argumentation, exactly what you mean. But again, what we're discussing here is the properties of a Hamiltonian. And Hamiltonian, you know, the Hamiltonian just describes the energy spectrum of a system. So it might be connected to a bath or whatever. Okay?
Sure.
Okay, now let's take a 15-minute break. And after the break, what we're going to do is what is known as Wilsonian energy.
Can I have a question?
That means, okay, let me just complete the sentence. That means that we're going to do this coarse graining in momentum space. Yes, what's the question?
I'm not sure where in our analysis in the example, we assumed that we are doing RG in the region J is much bigger than H. Like, when exactly did we do it? Assume this?
So what you can see here is that basically the spectrum of this block Hamiltonian is split into two states that are low in energy and two states that are high in energy. Right? So you have like two states. And then two states that are high in energy. And the distance between them is 2J. Okay? And the physics that's going to affect locally here between them is of order H. Right?
Okay.
So for this procedure to be accurate, for example, when I neglected this E here, I neglected this E, I actually cheated because this elimination procedure that I did here is not something that you can generally do, right? Because you're trying to solve Schrodinger equation. Schrodinger equation has E here and has E here. What I did was effectively throw away the E on this side because I said E is much smaller. Oh, sorry. E is much smaller than J. That was the justification because we're looking at energies. We're looking at physics here. At this scale here, which is much smaller than J. And that was our justification. But you can't do that generally. Okay, and it only becomes justified if you have this large scale. Basically, if you look at this term for a moment, see this term? It's basically second order perturbation theory, right? It describes basically the matrix element to go from here to here is H. The energy denominator is basically J. So what we're describing is, you see, there are two types of processes you can do. You can either go up here and then go down there, and that gives you a coupling between them, which is order H squared over J, and that's this term. But you can also go up here and go back down to the same state, which is also H squared over J, and that's this term here. And overall, what this implies is that this method of neglecting the energy in this elimination of states that I've done is valid only in the same regime where second order perturbation theory is valid. Because this is, you look at it, it's basically second order perturbation theory. And you can ask perturbation theory in what? Perturbation theory in H over J. Okay?
Could we done it like the other way around, like assuming that H is much bigger than J, and then the block will be E1 tilde and E2 tilde, up and down?
You can and you will.
Okay.
That will be your exercise. Okay? Okay, so let's go on a 15-minute break. Come back at 4:15. Go get something to להתרענן.
סבבה.
Okay, let me pause there. נמשיך את ההקלטה. Okay. Okay, so the idea behind the Wilsonian RG approach is, this is the much more common, I would say, and powerful technique for translational invariant systems. So you'll find that the real space RG we just described, for example, is a powerful method in disordered, for example, in disordered spin chains, spin glasses, stuff like that. But if we're talking about some translationally invariant system, like quantum electrodynamics, Fermi liquids, all sorts of stuff like that, they don't have to be really translationally invariant, but to some extent, translationally invariant approximately, then we want to do the RG process in momentum space and not in a real space. And then the idea is that, when we did the procedure before, if I look at this thing, there are these kind of RG steps. Okay, sorry, this is the L. This is L is like the RG step. And we're jumping from like one to the other. And here, if you like, this is kind of the microscopic scale. And this, and over there, it's the thermodynamic limit, macro. Okay, we're growing. So it means that this essentially, the fact that there is a first step here actually implies that there is like a cutoff. That's where we start the method. So the same kind of thing happens in momentum space. You can imagine that we have some theory, okay? And we have some momenta, like K2 and K1. And then we define the simplest possible scenario is we define something like a sphere. And the radius of the sphere is something which we denote by lambda. And lambda can, for example, be 1 over A, this microscopic scale. Okay? And then what we're going to do is we want to do something that's similar to this coarse graining. Okay, so how do we do the coarse graining in this case? We define our moral grounds here. Okay, we define a small ring. Okay, let's call it ring. So we define a second radius. Let's call this lambda over B, right? Remember, B was like our stretching parameter, right? So X, remember that we went from like delta X to B times delta X being, the scale. Now it's kind of like delta K goes to delta K over B. And that makes perfect sense, right? Because if I'm shrinking the momenta, it's like stretching in real space because the momentum and position have this kind of a conjugate relationship that, a smaller momenta means larger length scales, okay? And then we have this kind of, maybe this is a bit too much. Then we have this kind of ring here. Okay, this ring of states is like what we're going to call fast modes. So everything in here we call fast, and everything in here we call slow. And then the way you do the same procedure of the RG is that this elimination that we did of the high energy states, we're going to do the same thing here. We're going to eliminate these fast modes and obtain a renormalized theory for the slow modes. So let's see how that works. First thing I want to mention is that if I have a field phi of k, then I can basically divide it into two regimes. So I have phi slow if k is smaller than lambda over b, and phi fast of k is if k is between lambda over b and lambda. And lambda is like our higher energy cutoff. Nothing exists. And again, b is some number larger than 1. Okay? Any questions up to now?
Didn't you say that we'll eliminate the fast ones?
Yes, we will. No. Right now I'm just dividing it.
Okay.
I didn't teach you yet how to eliminate. I'm just saying that in the same philosophy of what we had in the real space RG, where we eliminated these high energy states and obtained an effective low energy theory for this new block spins, we're going to do the same thing here. I just want to, kind of make a connection that, integrating out the very highest momenta is exactly like the coarse graining procedure, because the highest momenta are like the most rapidly varying features in the these are like contributions to fluctuations or spatial fluctuations that are very rapidly changing. And if I integrate them out, I get an effective theory that is actually describing only collective, motion of many degrees of freedom. Okay. So then if I look at a Gaussian theory, so let's do the RG of the Gaussian theory. It's kind of trivial. So if we have a Gaussian theory, then S is equal to an integral k smaller than lambda d dk, and we have 1/2 phi k, k squared plus r phi k, okay? Phi minus k, actually. I might forget that minus, remind me if I do. Yeah. And now the point, what's nice about the Gaussian theory is that you can see that because the Gaussian theory only couples k to another k, it basically splits naturally into two disconnected sectors. S0, let's call this S0 because it's the Gaussian theory, okay? S0 slow plus S0 fast, right? Which is where this guy is kind of the integral where k is smaller than lambda over b, d dk 1/2 phi k squared plus r phi minus k, and this guy is the integral where k is between lambda over b and lambda. Okay, so the first step of the RG, first step is to integrate out the fast modes. So we write something like, z is equal to integral d over phi. Oh, sorry, I forgot to mention. This is phi slow, this is phi fast. So integral over phi slow and phi fast. e to the minus s0 slow minus s0 fast. But when we do the integration, we basically get two completely decoupled theories, which is z fast times the integral d phi slow e to the minus s naught slow. And the z fast is nothing but the expectation value. Well, you know, just the Gaussian integral. Gaussian integral. Okay. Now the point is that because in this case F and S are completely decoupled sectors, this step of the RG is trivial. It doesn't modify the slow part. We will see in a moment that once we don't have a Gaussian theory, that's when they start affecting each other. Okay, and that's going to be interesting. But for now, this step of the RG was completely trivial. Okay. The second step of the RG is stretch. Okay, what do you mean stretch? So exactly like I redefine the space with this B parameter, now I'm going to find a new momentum K prime, which is B times K. Okay, and that means that if I have a theory which is K smaller than lambda over B, d dk 1/2 phi of K, K squared plus R phi minus K, then this thing is actually equal to K prime smaller than lambda. Okay, so now I've stretched, I've basically taken this, you know, this slow region here, okay, and I've stretched it out to the boundary, like redefine the coordinate such that it goes back to the same value outwards. Okay, stretching it. And as a function of this stretching, I'm going to have some tree-level renormalization of parameters. And in particular, what I'm going to have is I'm going to have phi k prime. And then I have here k prime squared over b to the power d plus 2 plus r over d phi of k minus k prime. Now, where did these, no, not d, b to the d, sorry, b to the d. Yes, now where did I get these factors of b, these powers of b? Well, I got them because, this is dk prime. It's because I changed variables and this k prime contributed this extra 2 factor. Okay? Now I'm almost done. So now the last step is and this step depends on the fixed point you chose, but you need to make the you know, in this case we're doing it around a Gaussian fixed point. So what you do is you redefine the fields like this. Phi prime of k prime is equal to b to the minus d plus 2 over 2 phi of k prime. Okay, so basically we are also shrinking, if you like, fields appropriately to absorb this factor here. Now, what it implies, okay, so first of all, let me write what you get. Okay, and then what you get is a theory that is, again, defined on the same cutoff, d dk prime, 1/2 phi prime of k prime. Okay, and then I have k prime squared plus, okay, so now I have what
B squared times R.
What? D squared.
B squared times R.
Oh, yeah, b squared times r. Thank you. Yes. Good. So, and we can call this thing r squared. Okay, r prime. So what you see is, but before I do that, you know what? Let me take that back. Hold on one moment. So what you see here is that I've now completed the RG process because I came back to a theory that looks exactly the same, and I've made sure that the fixed point part of the action, which in this case is this k squared term, maintain the same structure. The only thing that changed is this mass term. So what we have here for this mass term is that r prime is equal to b squared r. Okay, that's the equation that we got. Because this is a Gaussian theory, the only perturbation I have is r. That's the only thing I can consider. And what you see here is that, yeah, it is what it is. Okay. Yeah, now I want to make a few comments about that. The first comment is that we can write an RG equation, right? Because we can say that B is something like E to the DL. It's like an infinitesimally small change, which is something like 1 plus DL. And that implies that R at scale L plus DL is equal to 1 plus 2 times DL, R at scale L. And if I move things around, I get that dr dl is equal to 2r. And this is our equation. Okay? So first question, so what you can see basically is that r is always relevant. So if I plot, here I have r, here I have r equal to 0, and then I have runaway flows in both directions. Okay? And I can actually solve for r of L is equal to e to the 2L r of 0. So it's growing exponentially with this kind of rescaling. Okay, so that's one comment. The second comment is I want to talk about, you know, maybe just something about correlations and exponents, is that we can also deduce what is the scaling in real space by looking at the Fourier transform, right? Because phi of r is equal to an integral d dk e to the I k r phi of k. Now we can use the RG transformation. So this is like d dk prime over b to the d. okay? E to the I k prime r prime. So I rescale both r and k together. And because I'm stretching one and shrinking the other, they compensate for each other. And then I get b to the d plus 2 over 2 from the field, phi prime k prime, okay? And then this thing is exactly, b to the minus d minus 2 over 2 phi prime of r prime. So what we find overall is that there's a relationship phi b to the minus d minus 2 over 2 phi prime of r prime. So what that implies is that if I look at correlation functions...
Can you explain why r prime is rescale like k prime? Because previously we saw it rescale like quadratically with b.
Oh, this is bad. This is bad. No, this is... That's not the same r. Let's call it x. Okay, it's a coordinate. It's like space. It's a Fourier transform. It's r here is a perturbation in the theory. Something else. It's a master.
Okay.
Sorry. But what I wanted to say is that g of r, which is something like phi of r, phi of 0. Okay, this thing will now be equal to b to the minus d minus 2 g prime of r prime. Okay, so we can use this because we know how the fields kind of rescale. And generally we can denote this exponent delta is equal to d minus 2 in our case. But generally what we denote is that delta is d minus 2 plus eta. This is known as the anomalous dimension. And now dimension. And the point is that because we're at a Gaussian fixed point, then eta is equal to 0. There is no anomalous dimension. And the scaling of the Green's function is exactly 1 over b to the d minus 2 in real space. But just to point out, for a general fixed point, you can have deviations. That's like just one critical exponent, where RG can give you how correlations depend on space. It can also give you other things, but I'm not getting into that. Okay, good. So that's the Gaussian theory. Now let's move to the fight of the fourth field theory.
Where did we assume in our calculation that we are in a fixed point, like?
Good question. So the fixed point around which we're flowing is this fixed point. Where did we assume that? Well, we assumed that here. You see, this redefinition of the fields is our choice. How did we choose it? We chose it such that this term is invariant, okay? And what we mean is that that part of the action, if we define the RG transformation the way I just did, that part of the action is actually invariant under the transformation. And that's, by the way, why they call it the renormalization group, because they look at it as if it's a transformation that leaves the action invariant. Okay?
Like what's the
What's the what?
transformation?
So we redefined our fields, you see?
Yes, that's
Okay. This redefinition was not chosen arbitrarily. It was chosen exactly to make this term in the action, okay, invariant under the transformation.
okay. Yeah, that I see. Yeah.
And that means that this part is our fixed point.
Yeah.
That's why this is the fixed point. Because if you park here, you're fixed, right? I defined the RG transformation in a way that if you start from R equal to 0, you'll stay there. You won't flow anywhere. Is that clear? You can also see it from the RG equation. Look at the RG equation. See? If R is equal to 0, nothing happens. Is that clear or not?
Yeah.
If it's not, then don't be shy.
Like a kind of subtle, like what you said is that you wanted that when we are in the fixed point, then the Lagrangian is invariant. That's what we wanted.
Well, wait a second. We define the fixed point that we choose is our choice, okay? Basically, you can think about it this way. You divide your action into like fixed point part, which is typically just the Gaussian part, okay? And a bunch of perturbations, okay, or couplings, we call them. And then when you nullify, okay, and now all these couplings, they flow under the RG. So when you do the RG transformation, they change. But the whole point of the fixed point part of your action is that you define it in such a way that it doesn't change. For example, in this case, I could have chosen the fixed point differently. See, I could have not had this 2 here and only absorb this. And then I could make this part of the action fixed. And then what I would find is that this guy is actually irrelevant. I'd find that I'd have to define, a coupling, let's call it C squared or something. And I'd find that dC squared dL is minus 2C squared. That's what I would find. I would find that around the massive fixed point, the velocity or the coefficient in stiffness, I don't know, the coefficient in front of the K squared term is irrelevant. You see, so it's basically my choice what is a fixed point or what is not. But once I chose that fixed point, then this redefinition. So I could choose this to be my fixed point or this part to be my fixed point. But once I chose one of them, I redefine the fields in such a way that that part of the action stays invariant under the RG, and hence the term fixed point, right? Because it means that, if that part is the only thing you have in your theory, that's the fixed point basically, then it's fixed. It doesn't flow. Is that clear?
Yeah, that's better.
It's not clear, but it's better.
Yeah, it's kind of a hard subject, but eventually I will understand it maybe.
No, don't be shy to ask. I agree. It's confusing.
Yeah, I think now I'm to the point that I'm not sure what to ask. So
Well, it's like imagine. Okay, let's get back to that point in a second. Let me add another term, another perturbation. Okay, and then it's going to be a little bit easier for us.
Can I ask a question before?
Yes.
Is there a general way to maybe know if the fixed point is a stable fixed point or an unstable fixed point? I mean, if there is a small perturbation, it will easily flow to another direction, or it will go back to the fixed point.
That's the whole point of that's it. You just described, like, you know, basically that's the work we have to do. That's what to like maybe to like the lowest order. So in the end, what we do is we derive our G equations, and then what you're describing is linearization of the RG equations around the fixed point. So you can linearize them around the fixed point, and then you just have you know, directions. So if the eigenvalue of this linearized matrix thing is a positive eigenvalue, it means that you're flowing away. It's what we call a relevant direction. And if the eigenvalue is negative, that implies that that's an irrelevant direction. So you're basically flowing in that regime towards the fixed point. Now, if you're flowing in everywhere, you're flowing towards the fixed point, then it's a stable fixed point. Okay. If you're flowing away from the fixed point everywhere, it's an unstable fixed point. But if there are like relevant and irrelevant directions, then it's you know, more complicated.
Yeah.
And in this specific case, like in a fight of the fourth field theory kind of thing, it's kind of general, like this R is what we typically call the tuning parameter, because it tunes us between positive and negative mass. And as you know, negative mass is like an instability in the Ginsburg-Landau theory, and positive mass is like a stable. So you can think of R as like a tuning parameter between two phases. And then the tuning parameter in phase transitions is kind of generically always just relevant. It's a relevant perturbation. So typically we don't consider you know, this direction as an instability. What you'll often do is you'll look in the manifold of R equal to 0, which is like the critical manifold, or the separatrix, if you like, between order and disorder. And then if you find fixed points on this manifold, then you can really get, you know, this kind of behavior where you have stable and unstable fixed points. But with R, it's kind of difficult to have a really stable fixed point because it doesn't really have a meaning.
Yeah. Okay, thank you.
Okay, so the fight of the fourth field theory. So what we're adding this term to the action. And I'm writing it in real space first. Notice that I'm using a slightly different notation than what we used when we studied the Feynman diagrams. So instead of 4 factorial, I'm writing 4. Why? Because I want to make your life hard. Let's call this X, because you said that I confused it. Okay. And now we can also write this in momentum space. By the way, each DDK like that has a 1 over 2 pi to the power of D. But I think that at this stage of the course, you can allow me to use units where pi is equal to 1/2, right? Thanks. Oh, wait a second. I need to, hold on. Let's take a short break because I need to arrange for electricity here. Hold on one moment. Zoom, okay. Okay, so yeah, I was, so we have, you know, these 4 guys here. Then we have a delta function D sum over j, k, j. So conservation of momenta coming from the fact that the interaction is local. Then we have phi k1, phi k2, phi k3, and phi k4. Good. Now let's see how we continue. The first thing we need to know about this is how does it stretch? So let's say I stretch the momenta. This is called the tree level RG process. Then let's see how I stretch it. So I write u over 4. The integral, pi j equal to 1 to 4. And then I have d dk j prime 1 over b to the power of 4d, because I have d dimensions and 4 momenta, and then I have basically b to the power of d times delta d sum over j k prime j. So the delta function has units, unfortunately. So that gave us this guy here. And then finally, the fields also have powers of b because I changed the fields. So I get a b to the power of 4 times d plus 2 over 2. That was the dimension of the fields. And then I have phi prime k1 prime phi prime 2. You know what, I'm tired of all these k's. Let's just call them 1, 2, 3, and 4. Okay? And that
you already integrate out the fast mode, right?
No. I haven't integrated out the fast modes. Let's assume I integrated out the fast modes, but I didn't really take that into account yet. That will be more complicated, because if you remember last time when we integrated out the fast modes, they were completely decoupled from the slow mode, so they didn't affect the slow part of the theory. But this time, they obviously have couplings through this kind of 4 field interaction. But I know that even if they wouldn't be coupled, just the stretching has an effect. And what I'm doing right now is I want to understand what that effect is. Okay, so I'm just stretching. You'll see in a moment what I mean by that, or why it's important. But bear with me a second. Basically, what I want to argue is that this thing is equal to b. So if I add, if I add 4d to 2d, let me count powers of b, okay? So I have 4d plus, sorry, I have a minus 4d, because it's 1 over b, plus d, plus 2d plus 4, right? And then this whole thing gives me 4 minus d. So overall, what I want to argue is that S4 prime becomes u prime over 4, right? Pi d dk prime j, delta d sum over j k prime j, phi prime, 1, 2, 3, 4. And I get, thank you very much. I get that u prime is equal to b to the power of 4 minus d u, and if I make this, b equal to e to the dl and make it like a small infinitesimal change, then I get that the u dl at this level is 4 minus d u. Okay, so this, what we have here is a tree level. Why is it called tree level? It's called tree level because diagrammatically, okay, let's put it aside why, in a moment, you'll see why we call it tree level. But the point is that this is like the lowest order term. It comes only from the stretching part. And here we really see this special behavior. We see that depending on the dimension, this perturbation can be either relevant, irrelevant, and marginal. And we find that there is what we call the upper critical dimension is 4. So above the upper critical dimension, these interactions are irrelevant, and one can argue, I might do that later, might do that in your exercise actually, that the upper critical dimension, sorry, d larger than the upper critical dimension, mean field theory exponents are the critical exponents. So if we think about this as a Ginzburg-Landau theory now with phi to the 4th and phi squared term, and we analyze, the critical exponents, like, for example, that like phi is, minus r over 2, over u in this case, then this implies that we have this beta exponent equal to 1/2. The exponent beta. Or if we look at, 1 over, like the correlation function g, right, is k squared plus r, which means that we have a correlation length, which goes like square root of r, which is like 1 over square root of r, and that, for example, implies that, the critical exponent nu is 1/2. Okay, these are all exponents of the mean field theory, and they're basically accurate. They become accurate when the interaction term is irrelevant and the entire vicinity of the critical point is controlled just by this r. And I'm putting aside here some issue related to dangerously irrelevant terms, but besides that, which really doesn't change this conclusion, that when you're above the upper critical dimension, then basically mean field theory gives the accurate critical exponents. But what we want to do is we want to argue that basically there is some O of u squared here, and that's exactly what we're after. We want to obtain the O of u squared. We also have this dr dl, which we just found is 2r, which is also plus O of, say, u squared. Okay? And we want to compute that.
I also know that above dimension 4, phi to the 4th is not renormalizable.
It's not renormalizable. Maybe that's this issue with renormalizable. Why is that? I don't. Okay, I'll check that. But it might be exactly this issue that above the upper critical dimension, there are these what is known as dangerously irrelevant terms. So if you kind of naively interpret the critical exponents from the scaling of the fields, you won't get the right critical exponents. You have to be more careful than that. I don't know if that's what they call not renormalizable. But if I remember from my high energy courses, I think that when in high energy, when they say that a theory is not renormalizable, it's actually when it flows to strong coupling, isn't it? And it might be related to the fact that you know that there's a difference, there's a fundamental difference between high energy and low energy physics. Like condensed matter physicists, they tend to look at low energy and long wavelength because we're after, you know, the collective, you know, emergent phenomena of, you know, many body systems, while in high energy, they say, okay, we live in some energy scale, you know, I don't know, like 300 Kelvin here and do our experiments, but we want to know the, you know, the laws of the universe, say, in the Big Bang or, you know, at the smallest, at the Planck scale or something. So they do the opposite. They flow to like short wavelengths and huge energy scales. And you can do that. It just means that L, instead of making L larger, you're making it smaller. And instead of coarse graining, you're actually dissecting. You know, you're taking these squares and making them smaller and smaller and smaller until you reach the microscopic, you know, Planck scale or whatever. And that is completely consistent with what you just said, because indeed, if you would flow L in the opposite direction, then you see that actually a negative beta function is actually relevant, right? And a positive beta function would be irrelevant. And then indeed, at dimensions larger than 4, you know, the fight of the fourth field theory, if you go to higher and higher energy scales, flows to strong coupling and is not renormalizable. I think that's what they mean by that. But of course, you've been contaminated with these ridiculous high energy ideas because you read too much of, you know, Peskin, and that's not the way we like to think about it. Okay.
Yes, when the Iranian attack started, and they told us not to come to the base, and I knew that I'm gonna have a renormalization course today. So all the week I learned from Peskin about renormalization.
Oh, I see. What race?
What?
Ah, you mean in the army where
Yes.
you didn't have to go
Yes, they told us not to come because of
because no one needs you guys actually.
yeah, exactly. Oh, guys.
or any other time for that purpose. So so I see. Very interesting. Yeah, exactly. So yeah, so it's really, so it's one of these things that condensed matter and high energy physicists like to joke around about, that, you know, we do RG in the opposite directions. It's kind of a joke, but yeah. Okay. So, okay, good. I'm happy we settled that. And tree level. Okay, that's not so interesting.
Also, at tree level, there's no fast modes, right? That's exactly
What?
what we're computing. At tree level, there are no fast modes. Everything is slow, right?
I don't know. We'll see in a moment. Now let's do the next step of RG, which is actually the first step of RG. Okay, so like you said, however, when we integrate out the fast modes in step 1, we generate additional terms. So the way to think about it is that if S0 divides into S0 fast and S0 slow, then S interaction, oh, by the way, did I call this S4? Oh, I called it S4. Okay, let's stick to that notation. Then S4 splits into S4 SS and is anti-Semitic, SF and S4FF. Okay, so basically this part is going to create a coupling between these two, and they're going to affect each other. And let's see how that thing works. So imagine that we want to compute, for example, the partition function, but only integrate over the fast nodes. So we want to compute something like df fast, d phi fast over e to the minus s naught fast minus s4 s fast. And then in principle, we also have minus s fast 4. But because our fixed point is the Gaussian fixed point, we're not going to take into account the effects of this S fast here. We're treating it as a perturbation. It may appear at higher orders, okay? But at this order, we can safely neglect this. Okay, if you like, this term is already proportional to U, and yeah. So right now we're going to neglect this term. Okay, good. So basically, this expression is equal to e to the minus S4 SF and taken with the Gaussian theory. So this 0 here denotes the fact that we're computing this with respect to the Gaussian fixed point theory. Okay, now how do we compute that? Well, okay, so that implies that our new action, S prime, slow after the integration out, okay, is S0S plus SIS S minus the logarithm of e to the minus S4I, not minus, sorry, 4. So instead we're going to call it 4. Let's call it 4 F0 like this. Okay, so this is the guy we want to compute. Okay, and we're computing it, the expectation value within the fast modes. Okay, so how do we do such a computation? Well, e to the minus S4 SF, because we're computing it within a Gaussian theory, we can use the cumulant expansion. So the cumulant expansion means that we basically write this as an exponent of C, where C is this sum of the cumulants. It's S4SF 0 plus 1/2 S4 SF squared minus S4 SF squared minus 1/3 factorial S4 SF cubed minus 3 S4 SF squared S4 SF and then plus 2 S4 SF All of these are taken with a zero theory, zero cubed, and so on and so forth. This is the commulant expansion. And the nice thing about this commulant expansion, we'll see it in a moment, is that all these additional comulants, like this, sorry, all these comulants in the end, they become like a fluctuation such that the terms you subtract are exactly the disconnected diagrams. We'll see it in a moment. But let's take term by term. So basically, all we really need to do is compute these comulants. And now you might notice that these comulants are exactly identical in structure to the things that we calculated when we learned Feynman diagrams and perturbation theory using Feynman diagrams, right? Because it's exactly powers of this quartic term. So we kind of have experience with that. Let's see how that works. So let's start from the first term, this. So what we're going to do now is we're going to calculate this commulant and this commulant. Okay, and that's where we're going to stop. Not going to do any more. Okay?
Can I have a question?
Yes.
Why do we have the LAN above? I'm not sure.
Oh, that's trivial because the full theory, okay? Let me write the full theory. The full theory is an integral d phi fast and phi slow. Sorry, by the way. Right? And then we have e to the minus s naught fast minus s naught slow minus s for fast minus s for slow fast minus s for slow. Now I'm integrating. So first thing, I'm neglecting this thing because I'm thinking about energy scales that are, say, very large, where this perturbation is still not important. And then I'm left with these other terms, and I integrate over. So I'm going to get something like an integral over d phi slow. I'm integrating over the fast modes, and then I get e to the minus s0s minus s0ss, okay? Times this e to the minus s slow fast, sorry, s for slow fast. Oh, sorry, this is 0, and then I'm just re-exponentiating this into the, and then I get the effective action. This is this guy.
Okay, thanks.
Okay, and by the way, I should add that here I also need to kind of restretch this and restretch that. So if I'm already calling it prime. So basically this term, you see, is going to be restretched and is going to give us exactly this part of the equation. And this guy is going to give us like higher
orders. Like what?
Higher orders. It's going to give us higher orders.
Also, by the way, like if you have high, if you said that you neglect the SFF because you're looking at high energy, but fast modes shouldn't have higher energy.
No, but that's exactly the point. Exactly the point is that think about, for example, the propagator. Okay, so the propagator has this 1 over k squared plus r, okay? And let's imagine that, you know, we're doing k is kind of the order of lambda. So I'm assuming that r is much smaller than lambda and that u is much smaller than lambda in the right units. They don't have the right units, but you kind of understand what I mean. If you make them dimensionless, then they're much smaller than the relevant scale at the cutoff. So I'm looking at very large k, where these terms are still considered to be small. See, I'm integrating out very, very high energy states. I'm just doing like a small step. So I'm treating all these perturbations, like small perturbations, and I'm seeing how they evolve under a small rescaling, an infinitesimal rescaling. I'm just looking at a tendency, like a flow towards a direction. And then I want to infer from it something. Okay? So that's kind of the philosophy. So imagine that U and R are small, and I'm integrating out the shell at very, very high moment energy, basically. Is that clear? You know what? Maybe forget about the Green's function. Maybe a better way to think about it is just the action, right? The action has, you have something like phi k squared plus r phi minus k, and then you have the the interaction, like phi 1, phi 2, phi 3, phi 4. What I'm trying to say is that when this k is very large, it's the most important thing. So it means that at very, very high momenta, the effects of R and U are negligible.
Okay.
It's basically like a free wave.
Okay.
And all I'm doing is I'm integrating a small shell there, and I want to see how this R and how this U kind of change infinitesimally when I integrate this small shell. Now, I'm assuming that every time I'm doing this RG transformation, they're still small. But then I see that they start to pick up, maybe one of them is flowing. And that gives me this kind of, if I have a runaway flow, that kind of justifies this idea that, if U or R become too big, there is no longer a justification to perform RG, right? You need to stop the flow. The flow is no longer valid.
And the formula for C is like a standard.
Yeah, commutant expansion is totally. By the way, it's kind of related to Wick's theorem in a way, but yeah, it's a standard expression that if you're looking at e to the minus, some function of a Gaussian variable, and you're taking expectation value over that Gaussian variable, you'll get this. Okay?
Okay, good.
Okay, so now let's see one of these guys. Let's start from this guy. So diagrammatically, you can understand exactly what this diagram is, right? So let's assume that like blue lines are low energy states or like slow modes, and red are high energy states, right? Then this is the diagram we need to compute, right? So this thing is equal to, okay, we have U over 4 from the coupling. There's one coupling here, U over 4. And then we have the symmetry factor. So thanks to Tzvi, we know how to do symmetry factors. So if we have, we have the vertex and this, then this connection gives us a factor of 4. This connection gives us a factor of 3, and this doesn't give us anything. So we have 4 times 3, okay, for the symmetry factor. And then we have an integral, lambda over b smaller than k, smaller than lambda, d k over 2 pi to the d. And then I have 1 over k squared plus r, okay? Now I can, I'm assuming that the theory is, hold on one moment. Okay, I'm assuming that the theory is rotationally invariant. So I do the angular integral, and I get s d minus 1, which is the I'll write in a moment what SD to the -1 is, but it's basically the unit sphere area in d dimensions, okay? And then this is divided by 2 pi to the d, an integral from lambda over b to lambda dk, k to the d -1 divided by k squared plus r. Okay, and this SD -1 is 2 pi d over 2 divided by gamma of d over 2. Okay, good. So now we have all this stuff.
Can
Now,
I ask a
yes,
question?
yes.
The line is red and the bubble is blue.
This is a slow, it's fast.
Yes, but you can change them and it will be exactly the same diagram, but
No. First of all, let's start from the fact that we're not integrating over the slow modes. So I don't even know what that would mean, because this loop that you have is an integral. It's an integral I'm performing. And I remind you that I perform only the integrals over the fast modes. So no.
okay.
And second, I'm looking for the renormalization of the slow theory due to integration out of the fast modes. So
Okay.
good. Okay, good.
But then you don't really have symmetry if you can't switch between them, right?
Symmetry. Who
Yeah,
said
like symmetry.
what?
The symmetry factor. The symmetry factor.
Oh, no, that's not true, because I want to remind you that, okay, now you have to be careful, because you see, when I write this interaction term, or here, let's look at this guy. Each one of these k's can either be slow or fast, or slow or fast. In fact, you can think about, opening each one of these guys into, phi fast plus phi slow. And then the symmetry factor is just the different combinations of, who you take to be slow and who you take to be fast.
And then we care really only on the integral on the fast ones.
Yeah, we're performing the integral over the fast ones, but you see that here it's like if you want to have 2 fast and 2 slow terms, then you have like 4 over 2, 4, like 4 choose 2, right? Different terms. And when I calculated that symmetry factor, I basically counted all these different terms. Okay.
I'm still not sure why the integral is only on the fast ones. If
okay. Let's first of all, the whole point is that we're integrating out only the fast modes. So that's first of all a statement, right? So this is this whole business I wrote. Where was it? Here. See? This is like Z. My original Z is this. But I want to obtain an effective action for the slow modes after I integrate out the fast modes. See? So I'm integrating over only the fast modes. I don't want, look, you need to think about it this way. If I could do the integral over the slow modes as well, then I might as well not do RG. It means that I know how to do this integral. But the whole point is that I don't know how to do this integral because it's an interacting theory and it's complicated. So instead, what I'm doing is I'm integrating a small shell of fast modes and see how it normalizes the slow theory. This is the philosophy.
so, this 0 is like 0 fast.
Yes, 0 fast.
Okay, good.
Yeah, I'm sorry, my notations are not so good, but yeah, totally. Like that's what I meant, also here. integrating only over the, I never integrate over the slope modes, never. Okay. Okay, wait a second, I forgot here some coefficients. So this thing becomes 3 times u. Okay, good. Now I just want to comment that if you have an integral, okay, so first of all, let's assume again that b is an infinitesimal thing. Then this integral has the structure of like lambda times 1 minus dl up to lambda, okay, dk over some function of k. Now, what does this integral give us? This integral is like the inverse derivative of f of k, right? The integral between lambda and f of lambda times 1 minus dl, which is more or less like f of lambda times lambda dl. So it means that we don't really need to do this integral at all. Like the integrand gives us everything we need to know, right? So this whole thing was like comment, and then we have that this thing is more or less, let's write it like this, 3u s d minus 1 divided by 2 pi d, and then we have lambda to the d divided by lambda squared plus r dl. Okay, so this implies that and you see that this term basically has two slow modes. So it normalizes the mass term. So what I want to argue is that now dr dl, which was 2r up to tree level, now we get plus. Now, why do I get plus? Okay, here it's important, the plus thing, because you see in this cumulant expansion, this guy comes with a minus. And then there's another minus here. So when I take the logarithm, I get 3usd minus 1 divided by 2 pi to the d. Then I have this lambda to the d, lambda squared plus r. Yeah, that's it. Okay, now let's do the other cumulant. Actually, I'm kind of running out of time. Let me just quickly write this. So I'm gonna do this cumulant, copy. Okay, and this diagram, maybe you guys wanna tell me what kind. So first of all, you know, here we have like two vertices. Let's not make them blue, sorry, it's a bit confusing. Here I have two vertices, and then I can connect them in two different ways. Like I can connect them like this, or I can connect them like this. But the whole point is that you see this guy here? He exactly cancels these. So I stay only with a connected diagram. So basically the only thing I really have is like 4 slow modes like this, connected with a loop of fast modes, a fast loop. So this is the diagram I need to compute. Easy peasy Japanesey. Okay. And now let's do the symmetry factor. So we have 4 external lines. We have two internal thingy-majiggers. And then, you know, I have a factor of 2 initially with which one I start. And then this gives me 2 times 4. This guy gives me 3. This guy gives me 4. This guy gives me 3. And then in principle, I get here 2, but it's canceled by the fact that I can flip. So overall, if I did this correctly, I get 4 times 4 times 3 times 3 times 2. And that whole thing is multiplied by u squared divided by 2. This coming from this 1/2. And then times 16 because I have 4 squared, and this gives me 9u squared. That's the coefficient in front of the thing. And therefore this diagram gives me 9u squared, the integral dk over 2 pi to the d, 1 over k squared plus r squared. Now is the time you should be complaining about something. Does anybody want to complain? No one wants to complain? Come on, I'm disappointed in you guys.
What, the divergence? Or...
No. Okay.
Is bigger?
No. What I wanted to say is that in principle, this is like...
the zero sound and BCS and...
What?
The way the momentum are arranged, like the zero sound and the BCS and these things.
What does it mean, the way that the momenta are arranged? What do you mean by that?
Like you can have 2 incoming momentum and 2 outgoing.
First of all, this is a scalar field. So there are no incoming or outgoing. They're just momenta.
Okay, right.
Everything is like incoming. But then you could have what?
Like in the same leg, let's say both are entering the diagram and the other side they're both...
No, but there is no entering or exiting. This is
Yeah.
So what I wanted to say is that if this is K2, K3, K4, for example, let's call it that way, then in principle, here we have a mess, right? Because, you know, we have, well, we don't really have directions, but you could imagine that if I want to conserve momentum, then I could call this, for example, K, but then this guy needs to be something like, you know, minus K1, minus K2, minus K, right? And then that implies that I should have a product of 2 Green's functions here, which is like 1 over K squared plus R times 1 over, you know, K1 plus K2 plus K squared plus R. And that's a much more complicated diagram to calculate, right? Because there are angles and it's a mess. But somehow I wrote this much simpler isotropic diagram. So what's going on? Why can I do that?
Because we are only interested in the modifications of the couplings, not in the full modification to the interaction.
Okay, that's also true. But in the spirit of this RG procedure, I want to remind you that we're doing very high energy. We're integrating out high energy and looking at low energy. That means that this K1 and K2, they're like slow modes. They're kind of, I want to think of them essentially Okay, actually, what Joseph said is more accurate. But let me first make my argument that this K, I want to think about it as being big, and these K's being small. Now, this is, of course, not an accurate statement because, as you see, this fast shell really reaches the slow mode. So if I'm thinking about momentum here and momentum here, they're actually pretty close. But then comes Joseph's argument. What Joseph is saying is that in principle, these couplings U and R, indeed, they can develop a K dependence. So you perform the RG transformation and they develop a K dependence. I didn't show this, but if you look at this expression here, where is this? Here. You see that any factor of K makes a term less relevant, right? This term went like K squared and was less relevant than R. And that means that these higher order terms, they're basically irrelevant under the RG. So that justifies neglecting the K dependence and actually only looking at the part of the vertex that doesn't depend on momenta at all. And that's why I neglect these guys. Okay. Good. And then let me just write the expression. So what we get in this case is 9st minus 1 divided by 2 pi to the d u squared lambda to the d divided by lambda squared plus r squared dl. And this implies that our equation for du dl is now 4 minus d times u minus this mess here. Okay, so now we can do an analysis. Basically, you see that the structure of these equations is something like dr dl is equal to 2r plus some a u, okay, or maybe I'll call it alpha, some alpha u, and du dl basically at low then we have 4 minus d u minus some beta, let's call it u squared. And if I plot this kind of flow in terms of r and u, then we get that for d larger than the upper critical dimension, which in this case is 4, we basically have a direction like this and a direction like that, and therefore the flow lines look like this, the streamlines. And for d smaller than the upper critical dimension, basically this this by the way is the Gaussian fixed point. And here what happens is that the Gaussian fixed point is unstable in all directions. Okay? Yeah. So what I'm going to show you, next week is what Kenneth Wilson and Michael Fisher thought of, which is a beautiful idea, is that actually if you, so when you go from, say, 4-dimension, say this is 4-dimension, and you go to 3-dimension, this thing is abrupt because it's an integer jump, and you go immediately from a Gaussian fixed point to suddenly to a runaway flow in all directions. But what they thought of, and we've written all the equations in such a way that we can easily do this. What they considered is the fact that you could actually change the dimension as a continuous parameter. So they actually made a much smaller step, which is they went from 4 to 4 minus epsilon. And then what they revealed is the emergence of a new non-Gaussian fixed point. So basically you have like, a fixed point like this. Then you have some flow. We'll do it next week. But the point is that using this is called an epsilon expansion. They were able to at least reveal some properties about the interacting case, and then there are some things you can learn from that, which is very interesting. That you can have access using RG to some non-trivial Gaussian fixed point. It's called the epsilon expansion. So what we still want to do is we want to do this 4 minus epsilon expansion, and also do fermions. So we want to do RG of fermions, which is a much more delicate issue, but we also want to do that. And how many more weeks do we have? 2? Or just next?
2 weeks. 2 more.
2 more Thursdays. Right?
Right.
So we if we'll finish the fermions next week, then we might do some topological field theories in the end. But if not, we'll probably end with RG. That'll be the end of our course. Okay?
Right.
So have a nice end. What?
I have 2 questions.
Yes.
Just
shame shame on you. Yes.
Why? But it's just the first one is just take a technical one. I'm not sure like how you jump. We did this expansion for the S, and then you jumped back to du to the L, but I'm not sure how, or the R to the L. I'm not sure how did you did this jump.
Okay. So I'll explain to you. We're basically talking about the key equation is this equation. Sorry, this equation. Okay, so imagine that I compute now, only this and this term. So I take the exponent. So I have minus ln of c. Minus ln of x. C is just minus c. So that means that these terms I've computed, this and this, they just add up to these terms. Okay. Now, how do I know which one is renormalized? Well, from the diagrams, I can see that this is a 4-field thing and this is a 2-field thing. So this renormalizes R and this guy renormalizes U. But I can do it more rigorously than that, because in the end, remember that you see this guy here has let me write it in full glory. I didn't write it in full glory, but just write like you could imagine that SF4 squared is something like d dkj pi j times pi j ddqj, right? And then we have like, let's call them phi 1, phi 2, phi 3, phi 4. And then let me denote the other guy with psi's, okay? Just so I can distinguish them, like psi 1, psi 2, psi 3, psi 4, okay? And now let's assume, I'm computing this diagram where I have, two Green's functions that are fast and outer legs which are slow. So let me assume that, I don't know, this guy is fast and these guys are fast. So these are like the contractions I'm computing. You see that I'm left over with these guys here. So I'm left over with a 4 fermion interaction, which is exactly these 4 legs, and they're slow, okay? So that means that this term, after I compute the expectation value over it's basically like computing this, 0, 0. Then basically what we're gonna get is an effective interaction. So that's why this term, if I plug it back in here, in this expression, maybe it'll be easier if I do the following thing. I can move this, I can write here, this thing is S0 prime S plus S4 SS minus C. So basically I computed the few couple of terms in this cumulant expansion. And for example, I just showed you that, for example, this guy normalizes the interaction.
Okay. Actually, in the expression of C, it's kind of interesting that you have an infinite series because you still have x of C and not just like the mean of the exponent is x of C and C is an infinite series. I would.
Why is that interesting?
Because E is an infinite series, but what you exponent like the exponent is not S is not an infinite series of S.
Right, but we're computing the expectation value over the exponent of minus x. That's why I get infinite series.
Because like if you expand XC in like with power series, then like you have an infinite series of
True.
in which in each term you have infinite.
Right.
Okay. But the second question, a more deep one, or Joseph, do you have something related to this? Or?
Like this is the thing that RG always give you other terms, right? It generates always something else. Like like many times it will vanish, but it always creates new terms to the Hamiltonian, right?
To the action.
Yeah.
So you must have infinite terms. That's what you are claiming.
Yeah.
Yes.
But usually they are less powerful. Yeah.
Okay. And the second question is like really why in what like I guess one of the reasons that we do renormalization is to get to treat like the infinite we get during our farm diagrams expression, right? This is somehow connected to this, but here we are kind of like from what I saw, this is a method for calculating stuff in certain areas of energy, like low energy, if we know the results in higher energy. Or
Wait, so the point is that these, okay. Good. So there is a divergence here lurking in darkness. And that's exactly let's look at this diagram for a moment. This is what you call dimensional analysis. So if you look at this diagram at d equal to 4, okay? So at d equal to 4, this guy goes like in integral dk k cubed, right? Divided by k squared plus r squared. So this thing in the end goes like an integral dk over k, which means that it diverges also in the IR limit. So it doesn't matter if you're doing a high energy RG and you're flowing to like you're decreasing L, or you're doing a condensed matter type RG and you're flowing to low energies. In both cases, these contributions are actually divergent in perturbation theory. So this RG, that's indeed something I didn't emphasize, gives us a method to incorporate the effect of these perturbations, despite the fact that perturbation theory diverges. That emphasizes the fact that it's a non-perturbative approach, which helps us deal with divergencies. And that's actually where it connects to QED, because one of the problems with quantum electrodynamics are that people notice that, you know, if you try to do perturbation theory, it's divergent. The question is, how do you deal with that? And RG is the method. That's the way to go. Okay? So the same kind of divergencies that you have in high energy, you have also here.
Good.
Okay, they're not special, those high energy physicists. They really aren't.
Yeah, I think we can continue this discussion maybe, but in another time. But
Okay. Okay. Good. So let's call it in a week, and you know, stay safe. Have a quiet weekend. I hope everything will be resolved soon. And yeah. Bye.
Bye.
bye. Wow,